Plinth beams are important structural elements. They are constructed at the plinth level, which is between the foundation and the walls. They form a crucial part of a building's base. Plinth beams effectively tie all the columns together, providing a continuous and level support for the walls built above them. A stable superstructure depends on well-built plinth beams. Plinth beams serve several vital functions. They distribute loads from the overlying walls, transferring these loads to the foundation. They also prevent differential settlement cracks which can propagate from the foundation upwards. Furthermore, plinth beams act as a damp-proof course, helping to stop ground moisture from rising. This effectively protects the walls from dampness. Concrete is a material strong in compression but weak in tension. Plinth beams are subjected to bending forces which create tensile stresses within the beam. Therefore, plain concrete alone is not suitable as it cannot adequately resist these tensile stresses. It requires reinforcement to handle such forces. This is where steel reinforcement becomes essential. Steel bars, often called reinforcement or rebar, are embedded within the concrete. This combination creates reinforced cement concrete, or RCC, which significantly enhances the plinth beam's strength. It allows the beam to resist tensile forces effectively. The steel and concrete work in unison, and this synergy is fundamental for structural integrity, ensuring the long-term durability of the plinth beam. Plinth beams are subjected to various types of forces. These forces include the dead load of the structure and live loads from occupancy. Uneven soil settlement beneath the foundation can occur, inducing significant stress in plinth beams. Bending moments and shear forces are common occurrences that constantly try to deform or break the beam. Steel reinforcement plays a critical role here. It is specifically designed to take up tensile stresses, which concrete by its nature cannot withstand. The steel bars embedded in the tension zone stretch slightly, preventing the concrete from cracking extensively. Without adequate steel, the plinth beam would fail under normal service loads. Steel ensures the overall structural integrity is maintained. Steel also imparts ductility to the plinth beams. Ductility is a very desirable property in structures, as it is the ability of a material to deform significantly under tensile stress before it fractures. This provides a crucial safety margin in buildings. If a beam is overloaded, it shows signs of distress, such as visible cracking or sagging, allowing for remedial action before catastrophic failure. Consider a plinth beam constructed without any steel. Such a beam would be extremely brittle and could fracture suddenly and without any warning, posing a significant risk to the building's occupants. This risk is especially high in earthquake-prone regions and areas with unstable soil conditions. Therefore, proper steel reinforcement is not just a recommendation, it is a fundamental necessity for safe and durable construction. Steel used for reinforcing concrete comes in different grades. The grade of steel indicates its yield strength, which is a critical mechanical property. Yield strength is the stress at which steel begins to deform plastically. Common steel grades are designated as Fe 415, Fe 500, and others like Fe 550 and Fe 600. The Fe symbol represents iron, the primary component of steel, and the number indicates the minimum yield strength in megapascals. Fe 415 was a very common grade for many years with a minimum yield strength of 415 megapascals. One of its main advantages is its relatively good ductility, meaning it can undergo considerable deformation before breaking. This property is beneficial during handling and bending on site. However, its strength is lower compared to newer grades, which might necessitate using a larger quantity of steel or larger cross-sections for members. Fe 500 grade steel is now widely adopted in construction. It possesses a minimum yield strength of 500 megapascals, making it significantly stronger than Fe 415 steel. Using Fe 500 can lead to a reduction in steel quantity, resulting in some cost savings. A variant, Fe 500D, is also commonly available. The D in Fe 500D signifies enhanced ductility, offering both high strength and good ductility. Fe 550 and Fe 600 are high-strength steel grades, with minimum yield strengths of 550 and 600 megapascals respectively. These grades provide even greater strength, allowing for further reductions in steel consumption and smaller concrete member sizes. However, these very high-strength steels typically exhibit lower ductility compared to Fe 415 or Fe 500D, requiring careful structural design and consideration. Selecting the appropriate steel grade involves a careful balance. Higher strength grades can mean using less steel volume, potentially reducing material costs and rebar congestion, which can make concrete placement difficult. However, very high-strength steel may have lower ductility. Lower strength grades, like Fe 415, are generally more ductile, providing more warning before any potential failure. But they might require a greater quantity of steel. For small residential buildings, consider the typical loads, usually single or double-story structures. Fe 415 or Fe 500 grades are often perfectly adequate, providing the necessary strength and being cost-effective. It is essential to always consult local building codes, as soil conditions at the site also play a crucial role. Stable soil might permit standard grade usage comfortably, but a consultation with a local structural engineer is advisable. For larger buildings, the structural demands are higher, including multi-story buildings or commercial complexes. Buildings located in earthquake-prone zones also need special care. In such cases, Fe 500D or Fe 550D are often preferred, offering an excellent combination of properties, balancing high strength with good ductility. This combination is crucial for ensuring seismic safety. A qualified structural engineer must perform the detailed design. In summary, plinth beams are vital for a building's stability, and steel reinforcement is what makes them strong and reliable. Understanding the different steel grades is important, with Fe 415, Fe 500, Fe 550, and their ductile variants existing. The choice depends on project-specific requirements, considering the building's size, design loads, and location. Always prioritize structural safety and long-term durability. Expert advice ensures a robust foundation and a secure building.